Line integrals, integrating not over an interval, but along a curve through a vector field. Imagine pushing a box along a winding path. A force field like wind changes direction as you move. How much total work did the force do? You add up F dot doctor along the entire path. That's a line integral. Here's a force field F equals y. Negative x. It rotates clockwise. Our path is a semicircle from the right, up through the top, and down to the left. How much work does the field do along this path? At each point, we compute F dot dr, the component of the force along the direction of motion. When the force aligns with movement, work is positive. When it opposes, work is negative. The line integral adds up all these tiny contributions. Watch the dot travel along the semicircle. The orange arrow is the force at each point. The work readout accumulates in real time. Notice, the force opposes the motion the entire way. So the work is negative. The field is fighting the path. The total work is negative 4 pi. About minus 12.57. Now here's the key insight. The answer depends on the path. The straight line from start to end gives zero work, because the force is perpendicular to the path the whole way. But the semicircle gave us negative 4 pi. Different paths. Completely different answers. That's why line integrals exist. There are actually two types of line integrals. The vector line integral computes work. F dot doctor. The scalar line integral integrates a scalar function along the curve. Like computing the mass of a wire with varying density. It uses ds, the arc length element, instead of doctor. A special case. Conservative fields. If the force is the gradient of some potential function, then the line integral only depends on the endpoints, not the path. The integral equals f at the end minus f at the start. Gravity is conservative. Our rotating field was not. Recap. A line integral adds up values along a curve, not over an interval. The vector line integral gives work. The force component along the path. In general, the answer depends on which path you take. But for conservative fields, only endpoints matter. These ideas connect to Green's theorem, Stokes' theorem, and the divergence theorem, the crown jewels of vector calculus. Thanks for watching. Subscribe to Zari Gatongi for more math explained visually. And visit 8gramswifi.org/math.